right, now we're going to back up and start talking about basics on heart muscle tissue again. We talked about this a little bit in AMP1. We're just going to review again. So, how do you recognize that this is cardiac muscle? It is striated just like skeletal muscle was. It is not multinucleated like skeletal muscle was. It does get those nice extra dark stripes, the intercalated or intercalated discs, whichever way you want to say that. So, cardiac muscle. Okay. One of the special features of cardiac muscle that skeletal muscle did not have is gap junctions. Now, back in skeletal muscle, we had motor units so that we could finely control how many muscle cells we could contract at one time so that we could grade a muscle contraction. Here in the heart, we don't want that. We want the heart to contract all at once, all the time. So we want all of the muscle cells to communicate with each other, and gap junctions allow that to happen. Okay. Next, what are some of the differences between skeletal muscle and cardiac muscle? So, one, means of stimulation. Already sort of mentioned motor units. Remember that you have somatic motor neurons that would release acetylcholine onto the motor end plate in skeletal muscle to tell a particular cell or a particular group of cells that it was time for them to contract. Here in the heart, while we do have connection to the nervous system just speeds up or slows down the heart. The heart beats on its own. That is called autorhythmicity. We'll define that again later on. So the heart does not need the nervous system to tell it what to do. It needs the nervous system to tell it how fast to go instead. Organ versus motor unit. So again, we want the heart to contract as one. We don't want twitchy little contractions. We don't grade the contractions like we did back in skeletal muscle either. And then last, in skeletal muscle, we had a pretty short refractory period where the muscle was not able to respond to another stimulus. Here in the heart, that would be bad. The heart needs time to fill with blood in between contractions, and so the refractory period is longer so that the heart has time to fill with blood before it contracts again to pump the blood. Okay. Autorhythmicity, defined that a second ago. So here you have a heart that has been removed for transplant purposes. Again, it is not connected to anybody's nervous system. It is connected to blood tubes because hearts have to have something to pump or they won't pump. And so that's what those tubes are for. But notice it's pumping on its own because it has autorhythmicity. It contracts on its own because it feels like it. And again, the nervous system just speeds it up or slows it down. This is the first time that I will mention this, but I will mention it again. Generally speaking, the nervous system slows the heart down. The heart wants to beat faster without the nervous system telling it what to do. Okay. The intrinsic cardiac conduction system is sort of the heart's own mini nervous system that allows the heart to control its own rhythm. There are several different parts to it. The SA node is arguably the most important part, but there are several other parts that we're going to talk about in a second. The AV node, the Purkinje fibers, all of those sorts of things. This is how the heart helps maintain its rhythm and make sure that we always have time to fill with blood before we pump and we have nice strong contractions. This is a heart that has been removed from a person, and hopefully you can see why. These are not nice, strong contractions anymore. This heart has a lot of fatty tissue. It's just not able to maintain blood pressure. Like, compare this heart to this heart. And which one would you rather have in your body to help you maintain your blood pressure? And I think it's pretty easy to see which one you'd rather have. This one's cardiac conduction system is not functioning very well anymore. Okay. Now, back in skeletal muscle, we had leakage channels, we had chemically regulated channels, we had voltage regulated channels. And we're going to have most of those again here in cardiac muscle. But one of the important things that we've got going on here that we didn't really have in skeletal muscle are these, let's focus on this stuff going on. We're going to have these leakage channels that are open that are going to allow us to constantly drift towards threshold. And then once we hit threshold, again, without the nervous system telling us to open doors, we hit threshold because of leakage channels, and that's what triggers the release of calcium. From there, it goes back to kind of like skeletal muscle. We bind to troponin, that pulls tropomyosin off binding sites. Myosin grabs actin and pulls. So from there, it's pretty much like skeletal muscle. But the mode of stimulation is different. Now, these pacemaker potentials, they are not happening all over the heart. They're happening specifically in these nodes, the SA node and the AV node, that help regulate when the heart will contract. The SA node tends to set a faster pace, and so this is where we tend to have the most leakage channels. It's going to help us hit threshold first, and then once the SA node fires off potentials, it makes everything else go because it wants to. It's the boss. It controls when everything else does what it wants to do. Okay. Next up, I gave you this picture. You're labeling everything that is in blue on that picture. So the parts that you need to know. The sinoatrial node, or the SA node, is the pacemaker of the heart. It has ultimate control over when the heart is going to beat, how fast it's going to beat, although again, the nervous system can speed it up or slow it down. It is not directly connected by fibers to the AV node, which is the atrioventricular node. So when the SA node fires off an impulse, it's going to take a little bit for that impulse to travel down to the AV node. That gives the atria time to actually depolarize and contract before the ventricles are going to do anything. So that delay is going to be important for us. Okay. The AV node, once it receives the signal, it's going to pass that signal through the atrioventricular bundle, which used to be called the bundle of His, but isn't called that anymore. So if you've ever heard of bundle of His, it is now called the atrioventricular bundle. The AV bundle splits into the right and left bundle branches, kind of like one for the right side, one for the left side. Not kind of like, it is like. Okay. Then, once we get to the apex of the heart, we get little branches that come off of there. The branches are the Purkinje fibers. It's always sort of interesting to watch how students like to say Purkinje. I've heard students say Purjunkie. I don't know how you get there, but no, Purkinje. Now, here's how I like to sort of say this. The fibers on the bundle and the bundle branches, they are like they're insulated. They are not causing depolarization events. We are not actually making the ventricles contract as the impulse is traveling down those bundles. As we get to the Purkinje fibers, though, then we get to uninsulated fibers. And so then we start to actually make the ventricles depolarize. And here's why that's important. Do you want your ventricles to contract from the top down? Absolutely not. There's not anywhere for the blood to go down here. So we don't want to squeeze from the top down. We need the ventricles to squeeze from the bottom up because our exit points are up here at the top. So the Purkinje fibers start at the bottom and then start our squeezing in the upward direction to make sure our blood gets squeezed from the bottom up so that we can leave through our semilunar valves and then up through the pulmonary trunk and the aorta, depending on which side we're on. So everything is arranged beautifully here to make sure we've got our gap between when the atria and the ventricles contract, and we are squeezing the ventricles from the bottom up. Okay. Normal rhythm. The SA node is what sets normal rhythm. I feel like there was something else I always wanted to say on the slide, but for the life of me, can't figure out what it was at this point. Hopefully it will come to me at this point. So SA node is setting it. Normal rhythm for heart rate is going to give you a pulse that is somewhere between 60 to 100 when you're at rest. All right, arrhythmia means that you have an abnormal rhythm, and that'll tend to mean like your heart's racing and then slow and then racing and then slow. Like as you're looking at this one, this person has a slower heart rate through here, and then it speeds up over here. And what's important about this is a person at rest. It's not like they were at rest here and then they started exercising. That would be normal. You're supposed to have your heart rate speed up as you're exercising. But if you're just sitting there and you're not being stimulated and your heart rate changes, that's an arrhythmia. Now, if a person has an arrhythmia that is interfering with quality of life or is full on a health risk being the important part here, then we do have artificial pacemakers. We'll hook it into where the SA nodes used to be. This is an x-ray to show you where they are, and I love this x-ray. I don't think people understand how pacemakers get implanted in there or the complications therein. I always like to start this with what gender is this person? Just because I like to see my students sort of stutter with things. So you guys think for yourselves and try to figure out what gender you think this person was, and then I'll tell you, here's your hint. That's a bra strap clasp. So yeah, this is a female. Here, of course, is your pacemaker. Here are the wires that's going to take us and connects us off to the heart. Here's your weird thing that nobody ever thinks about. This is battery operated. Those batteries have to be changed. That costs way more than you think it does in America. Okay, fibrillation. So we haven't really talked about what a normal EKG looks like just yet, but this ain't it. There are 3 normal deflections, 5 if you consider the QRS3. If you're not seeing all of those and they are not the normal measurements that you're supposed to see, then basically you have fibrillation going on. I want to rephrase that. Because there are certain times where you will not see the normal deflections, but we're not in full-on fibrillation. Fibrillation is, like I said on the slide, chaos. There's no normal rhythm. There are no normal deflections. You can't tell when a person's in QRS. You can't tell when their ventricles are depolarizing versus their atria. Like, you got no idea by reading it what's going on in that heart. That's when fibrillation is happening. Now, the note that I want to make here is one of the things that pisses off all medical personnel is whenever they watch some TV show and then it's, oh no, the person is flatlining, quick, grab the paddles. Okay, the paddles are defibrillators. You use defibrillators when a person is in fibrillation to stop them from fibrillating. You do not use paddles to bring a person back to life. They are not magical. We are not Dr. Frankenstein. We cannot do that. If a person is flatlining, you do chest compressions. You don't shock them. That is not how the world works. And so know that first and foremost. If a person is fibrillating, though, it means the SA node, the AV node, all of the heart's intrinsic conduction system, it's in chaos. Like, everything is battling for control and nobody is winning. So we grab the paddles to shock it, and it's sort of like trying to reboot a computer. It's trying to get the SA node back in control. And so you can see, boom, that is where we hit the person. Why is my thing not hidden? And you can see we're sort of trying to get back to normal. Now, this is not normal, but it's a lot more normal than we had going on off over here. And so this is when we defibrillate, is when a person is in fibrillation. All right. Your book sort of does things out of order here, and I'm not in love with it. So here's where I'm going to skip ahead for a second, and then we'll go back to the other things. This is a normal EKG. Now, disclaimer. EKGs were named based on the German. The K is for cardio. So in German, cardio is with a K and a little bit of anger. ECG is the Latin version. Most doctors still call it an EKG. I really don't care which one you call it. I'm old. I was taught EKG, and so that's still what I tend to do. So there's that note. Okay. The 3 basic deflections that you're going to see in an EKG are the P wave, the QRS complex, and then the T wave at the end. The easiest part of this to find every time without fail is the QRS complex, because it's the biggest spike that you have going on there. So when you're first trying to read EKGs, find your QRS complex and then start looking for all your other waves. So once you find those, you just sort of keep on reading and making sure we always have the other waves too. Okay. From there, here's what's going on during each of those waves that's so important. When the SA node fires, it starts a depolarization event, which is what's depicted as this yellowy orange up here. That depolarization event is the result of sodium and channels opening, calcium channels opening. That's electrical stuff, and the leads that are on the person pick that up, and you get this charge, this wave that you can see right here. So all of this is atrial depolarization that resulted from the SA node firing. So basically, if the P wave is good, it means the SA node and the atria are good. Now, after the SA node fires and our atria depolarize, next up our atria are going to contract and then repolarize. So one of the things that I need you guys to make sure you understand is depolarization is not the same thing as contraction. Repolarization is not the same thing as contraction. Depolarization triggers contraction. after contraction will repolarize. So between these two, that's when contraction is going to happen. Okay. Remember that repolarization is us putting our ions, well, getting our charge back to where they were supposed to be. That's potassium going out, if you remember that from skeletal muscle. As we are repolarizing the atria, this is also when the AV node starts to relay the signal through the AV bundle, the bundle branches, and then down to the Purkinje fibers. And the Purkinje fibers start to depolarize the atria, again, from the bottom up. So what's happening during the QRS complex is the atria are repolarizing and the ventricles are depolarizing. Since the ventricles are so big, this spike ends up being huge as the ventricles are depolarizing. Then we get a little gap. The ventricles start to repolarize, and then we get the T wave, which is when the ventricles repolarize. So if the QRS complex is good, it means our ventricles are depolarizing like they're supposed to, and our atria are repolarized like they were supposed to. If the T wave is good, our ventricles repolarize like they were supposed to. Okay, so coming back to this slide right here. So one of the things I said was find yourself a QRS complex and then read it from there. So there's a QRS, here's a T, we got a big old gap, and then a QRS again. So we're missing the P wave that is supposed to be right here. The P wave was supposed to go like that. Remember what's happening during the P wave is the SA node is firing and the atria are depolarizing. So if that's missing, it means the SA node ain't working like it's supposed to. So the SA node is non-functional. Since the SA node is what normally sets the heart rate and it's faster than everything else, that means the person's heart rate is going to be slower because now the AV node is in control. So this person is also going to usually exhibit what's known as bradycardia, which is a slower heart rate than normal. So we're missing a P wave and we have a slower heart rate. Next up, this one even starts with a QRS, makes it easy. So QRS, T, P, QRS, T, so far so good. P, nothing. P, QRS, T, P, nothing. So right here, we had a P wave that did not get relayed to the QRS and the T wave. So the SA node did what it was supposed to do. AV node ignored it. So, I don't really love how they say that. AV node is ignoring what the SA node is doing, so we're seeing more P waves than QRS waves. This is sometimes called the heart skipping a beat because the ventricles aren't pumping. They're missing sort of every other beat. It doesn't have to be every other. As long as we're missing some, that is heart block. Okay, we talked about that one earlier. So here I just pulled some different EKGs from off the internet so we could look at them. And so again, it's just find a QRS, trace it. So QRS, T, P, nothing. P, QRS, T. So remember, we lost something here. What was that called? That is heart block. Our AV node is ignoring what's going on. Hard to find anything to call a QRS wave there, so what would you guys say that is? That is fibrillation. Grab the paddles. Okay. QRS, T, P, QRS, T, P, QRS, T, P. We've traced this for a while now. Everything's good. So this is normal rhythm. QRS, T, nothing. QRS, T, nothing. QRS, T, nothing. All right, so we keep missing what's supposed to be here. What was that called? That was junctional rhythm. So make sure you can recognize all four of those. Okay. Heart sounds. Heart sounds you tend to listen to with the stethoscope. This is showing you where you can place the stethoscope to hear specific heart valves. When you listen to a heart, you should hear Lub Dub. You should not hear any additional sounds. If you do, it means one of the valves is not closing like it's supposed to. Sometimes you might hear Lub Dub. That tends to mean one of your AV valves didn't close correctly. Sometimes you'll hear Lub Dub. That tends to mean something else is going on. Once again, I usually show a video in class here, but I'll probably get copyright blocked if I post that. Let's see. See if I can make it stay there for a while in a place where it would be legible. Come on. You were there a second ago. Let me change my pointer options and see if I can get it to do it that way. Arrow options. Okay. Y'all can type that in if you want to go watch the video. The video, you do get to hear what normal heart sounds are, so you can get used to the normal heart sounds. And it shows you, I believe it's an S3 and an S4 murmur, so you can hear what those particular murmurs start to sound like. It is a doctor's job to diagnose a murmur, so I'm not asking you guys to be like, oh, that's definitely an S3 murmur. I do want you to be able to go, ooh, that's an abnormal heart sound, though. So you should know what normal is, and you should know what abnormal is, and you should know abnormal means a valve is not working correctly. So that's what I want you to be able to focus on here. Okay. Next. Systole and diastole is how you say these words. Systole is contraction of the heart. Diastole is relaxation of the heart. Once again, I usually show a video here. You can pause this and get the URL there so you can type that in and you can watch it. This one's a really boring book video that shows you the cardiac cycle and how it works. But again, I don't want to get copyright blocked so that you guys can't see it. So go watch that video should you want to. Now, I already have a video where I explain this picture and the cardiac cycle just a little bit. But after I made that video, I found this GIF, and I like this GIF just a little bit more. So here's what you need to understand about the cardiac cycle. You have to understand everything that is going on. What happens when the atria contract? What happens when the ventricles contract? When the ventricles contract, which valves close? Which valves open? When is pressure going to go up? When is pressure going to go down? When is the SA node going to fire? How is this going to relate to an EKG? So this GIF does not show you EKGs. It does show you, so phonocardiogram is just hearing heart sounds, and so the first sound is lub, the second sound is dub, third sound should not really be there, but that's all right. So lub dub, that's going to correspond to the AV valves closing, and then the semilunar valves closing, and so you can watch the video through multiple times and you will see it working exactly like what I just said. They're showing you pressure in the aorta. That's going to increase as the left ventricle contracts. Atrial pressure, that's going to increase when the atria contracts. Ventricular pressure, that's going to increase when the ventricles contract. Ventricular volume, this is one that's going to be important, and we're going to talk about that in the next video. I have to think about my stuff here. So the end diastolic volume is the amount of blood in the chamber just before it contracts. Then it contracts and pushes out as much blood as it can, and you are left with end systolic volume. The difference between those two gets you stroke volume. That is labeled, I think, on your book's picture, yeah, but it's labeled with abbreviations. So end diastolic, end systolic, and then stroke volume is on there. Oh yeah, the EKG is on here. Sorry, I didn't see that earlier. So the EKG is on here, and you can see P wave, QRS, T wave, so that you can see everything. Just watch that go through, and again, you can't really memorize the cardiac cycle because it's about understanding everything and how it all relates to everything else. And so watch the other video that I have posted. Ask questions about anything like, why is that valve closing at that time, if you need to. Notice that this GIF is showing you the pulmonary valve. You can't see the aortic. It's hiding behind the interventricular septum here in this picture. Weirdness in this GIF, it is showing you the AV bundle. It is not showing you that it splits into the bundle branches, so just note that there's a weird anatomy thing going on there. But aside from that, I do like that it's at least showing you ventricular contraction and then the valves and when they open and close. You can see the auricles. You can't really see the atria. Aside from, the auricles do mark where the atria are. I hope that helps you understand a little bit more about the cardiac cycle. And again, if you just Google that, you can find this GIF to run through it multiple times. And hopefully I've sat here jabbering long enough that you guys have sort of watched it run through enough times that you're sort of starting to get what's going on there with the cardiac cycle. It's tough to understand, totally get it. But I've got that other video posted, and I'm here to answer any questions you have.